10th exam has been moved to the Wednesday before that holiday, and will be just one day earlier. I had programmed in some leeway because I knew that I was going to go a little long. I wasn't going to be able to get some of these chapters as fast, and so that some of that leeway is already being eaten up. So that's one of the days. And then you remember when I wrote on the board that acronym for that thing, and I said, "What on earth does that S stand for?" Remember that?
You made it wrong.
Well, I wrote it wrong. It's not an S, it is indeed a C. Which makes sense, right? And for those of you who don't know what I'm talking about, look back in your notes, and it's it's one of the last things we talked about. Yeah, oh, here it is. It was the Food Allergen Consumer Protection Act. You know what? It's wrong on the dang slide. Can I see your pen for a minute? Thank you. So it's not FALSPA, it's FALCPA, which is exactly what you think it should be, right? Okay. The main thing I want you to know about some of those things we're talking about, I want you to be aware of the agencies that are working together, not only to protect our food from agro-terrorism across the world, but also just protect the safety of your food on a daily basis. And you know what, y'all? If you're one of those people who thinks that we have too much government involvement and you'd like less funding for those programs and you'd like it to be reduced, well then fine, you've got the right person in the White House right now. But if you aren't, if you promote someone watching out for the safety of our food, well then we have to pay the taxes that pay those people. And so we can't complain about, oh, where are our taxes going or what's the government doing, etc. So I'm not saying either way is correct, but I'm hoping to introduce you guys to some of these agencies so you see what they do, not only so that you'll know to support them or not in your future, but you may be working for one of them one day. You may decide that's what you want to do. Agro-terrorism. I can see a TV show now. Agent for the perversion of agro-terrorism. All right, anyway. Okay, so I want to finish up this chapter just very quickly talking about functional foods. And functional foods, along with the term nutraceuticals. I'm whispering, did I already do this? Okay. With nutraceuticals, these two really are talking about the same thing. And there is no legal definition for either of them. So when you see them on the web, or you read about them, or you see them in a paper that looks like they know how to create a look that looks like it's coming from some kind of peer-reviewed scientific journal. Read further, inquire more. It's easy to create a document that looks exactly like the ones that come out of scientific journals. So please be very, very careful. These two have no legal definition, but basically what we are defining them as consumers, okay, is these are foods that are assumed to provide health benefits beyond their nutritional or nutrient content. And you've heard some people refer to these as superfoods. And there's all kinds of fun things. If you Google, you don't have to Google it. I mean, you see superfoods everywhere. You see Dr. Oz talking about raspberry ketones and yada, yada, yada. You know, I'm throwing things at the TV when he does that. But it's sort of like this beyond. In fact, the police, do you guys even know who the police was? The police was a group that Sting led, the police. Don't stand so close to me. Every breath you take. You know that? All right, that's the police. All right. They did an album called Synergy when I was in grad school. Synergy. Does anyone know what that word means? And Sting was referring to this idea that sometimes things come together and the whole together becomes bigger than its parts. I am a musician, and so you'll hear me talking a lot about music, but if any of you are into like barbershop quartet kind of music, or if you've ever sung in a choir, there's something about these 4 parts that if they hit the harmonic exactly note, right, there's something called the 5th note that's created. The 5th note. And it's a note that nobody is singing, but it's the 4 of these notes individually coming together and creating a new something, the 5th note. And that's the ultimate compliment you can give a 4-part singing group, is that, they hit the 5th note. Get it? All right. All right. Well, there's some people who believe that these foods have a 5th note. There's something about their synergy. They come together and they create something. They provide something for our health that is beyond the nutrient content. I personally don't believe that. I'm a scientist. Just because we don't know what it is right now doesn't mean that there isn't something tangible. So I believe that we're going to find something. But anyway, these functional or nutraceuticals, as they're called, and you can put phytochemicals in this group. We can look at these functional groups, and I want just to give you a few things, a few examples of what are considered functional foods. And I will encourage you to look at tables 1.2, 1.3, and 1.4 in your text. I want you to know all of those. I want you to be familiar with all 3 of those tables. So anthocyanins, which pretty much are the pigments, these are those raspberry ketones that Oz was talking about. These you find in almost all your berries. That's why, like blueberries, raspberries, blackberries, these are all in the superfoods list, right? Okay. And then there are the isoflavones. And these are the things that we find in soy. All forms of soy. Tofu, tofu paste, okay, soy protein isolate, which is in many of your protein powders that some people use. So your isoflavones, and these isoflavones, that has an E on it, sorry. These tables go into more detail, and they tell you what the theory is of what these foods help prevent. Again, you notice I'm using the word theory, right? Okay, that doesn't mean it's fact yet, and doesn't mean it's wrong, but we've got to be very careful. And then there's the beta-glucan in oats. Now this one has a little bit more tangibility because this changes the solubility, the viscosity, if you will, of your gastrointestinal juices. And by doing so, it causes you to produce more stools, therefore you need more bile to make more stools, therefore you need more HDL to go out and sequester the cholesterol from LDLs and other non-hepatic, non-adipose tissue and take it back to the liver so bile salts can be made, so more stools can be made. So thereby, oats can be said to lower blood cholesterol. Did you guys get that? You got all that? Really? Wow. Good for you. All right, the main thing I want you to know is that that's why Cheerios can write on their box, may reduce cholesterol. And that's one that does have a little bit more proof. Okay, and then the last part of this chapter goes on pretty much into designer foods. And this is something that's been talked about quite a bit in metabolomics, and that is once we're able to decipher the human genome, once we're able to do that, you can even send your DNA now. My sister had it done. And she found out that we are like 49%, Irish, and the other like, Scott. And I could have told her that. But the point is that you can send in your DNA now, right? Now that we've done this. And there's this whole movement. And there's a Dr. Bruce, I can't remember his name now. He's famous, Dr. German, at UC Davis, who's very much into metabolomics. And that is, let's create the perfect diet for the perfect person. Once we understand their intermediary metabolism, we can now predict. In other words, we're not going to tell you need this many calories and this much blah, blah, blah based on Kathleen's dietetic formulas. Now we're going to take your DNA and we're going to tell you exactly how your intermediary metabolism spins. Now, first world, second world, or third world problem? Absolutely. So there's a whole schism at UC Davis. There's all of those, like I was in the international nutrition part, where we're like, I can't believe you're wasting money on that when so many people are starving. And then there's the other people who are saying, if we can do it, why not? Obesity is becoming a problem. Why not figure out the perfect diet? So your last part of your book talks about this nanotechnology. And this nanotechnology can be applied to medicine. There are physicians out there, or researchers, who are discovering exactly what kind of cancer you have, what little device we can send, a chip that can be put, say, in the spleen where you have cancer, and it can determine when to release the drug to kill those cancer cells. That's nanotechnology. There are foods now that have nanotechnology on them that they know when to release the pesticide. They know when to release the antibiotic to kill the staphylococcus that has invaded. This is all happening right now in food science. And I find it absolutely incredible. And of course, if they can do that for the safety of our food, clearly they can do it for the taste of our food. Do we need a little bit more moisture? And the nanotechnology, I encourage you to look at that last part of your chapter. You might be blown away at some of the jobs. I'm not going to be testing you over that. I think it's just there for your own edification. But it is fascinating. It does talk about the different jobs that are available in the food science world. It's not just the dietitian. In fact, we're really the edge, because most of us go clinical these days. But for food science, if you're interested, there is a ton of work that can be done, that is being done. Moving on. Was there anything that I was supposed to clear up this class besides that exam and that acronym? Yes.
So you did say there's quizzes for every Friday. I was looking at the syllabus. I didn't see the quizzes in the syllabus.
I don't care. I told you.
Oh.
I'm not going to write down quiz. Do you really need me to write on the syllabus quiz?
No.
Okay. You're so sweet. And probably half the people in here are glad you asked that question. But yeah, I may not write it on there, but yeah, you're getting a quiz every Friday. Okay. All right? Okay. Thank you, dear. Anything else that I was supposed to clear up? Seems like someone asked me the question at the end of last class, and I said, make sure you ask me that at the beginning of next class. Does anyone remember that? I guess it wasn't that big a deal. All right, let's go on to the next chapter, and we're looking at water. We're looking at water. Water, I know I always love talking about water. We all know water is H2O, darn it. We all know water is H2O, right? No carbon molecules. So is water, according to the scientific definition of organic, is water organic?
No.
Absolutely not. He's absolutely right. It is not organic. Okay, so when people say I'm going all organic, I like to say, so you're not having water? Okay. All right, so water is common in food. It's a common ingredient, a common constituent in all foods. As a matter of fact, I want you to think of the word carbohydrate. So like my athletes, I never let them abbreviate carbs because they are forgetting the most important part of the word, hydrate. You get up to 40% of your water from your carbohydrates. So when an athlete decides to forego carbohydrates or cut them down, I say, well, you're on a dehydration diet. So please be very, very careful. That's not a smart thing to do. And a high protein diet requires water. It requires more water. That's why when you're a high protein diet, you usually are thirsty, and I'm digressing to nutrition. All right, so water, as we know, has 3 states. And the most important reason for that is because of the structure of water. So you have oxygen. And if you remember from your chemistry, in its valence shell, in the Bohr model of the atom, you saw us coming back. You remember those P to S things you had to write? Yeah, I hated those too. So in that outer shell, oxygen has what valence? 6, exactly right. So therefore, it's going to have 3 pairs of electrons. Well, one of the bonds is going to be with one of its hydrogens. Hydrogen, therefore, is going to be sharing 1 electron. And then the other set is going to be with another hydrogen. This angle here is 105 degrees. This, is it 105? Yeah, that's right. Okay. There is a negative charge here and a positive charge here. So water is a what? It's a dipole. It is a dipole. And you always draw the dipole going toward the negative charge. Okay, so it has a dipole moment of 1.864 D. So the dipole moment of a normal, most compounds or what am I looking for? Yeah, compounds out there is 1. Water has 1, yes.
Not very important, but you're missing a pair of electrons.
Well, there's a pair here and a
No,
pair here.
there's 2 pairs of two lone pairs.
Oh, you're right. Thank you.
No problem.
Thank you. Okay, so we've got there we go. All right. Okay, so we've got and then when the dipole moment it's a product of the charges and the angle, the distance. So, or distance between those charges. And that's how you get the dipole moment. The whole point I'm trying to make here is that water has a large dipole moment compared to other compounds. This is an extremely polar molecule, and it's sticky. It's sticky. In other words, and you've heard about water's cohesiveness, right? The surface area, the surface tension, and all that. And it's because it's got positive charges and negative charges. It's pretty attractive to just about everything out there that's polar. Anything that has a charge, i.e. polar, water is attracted to. Therefore, it makes it the universal solvent. Exactly right. And the solvent means it's something I can dissolve in. So because of water and its wonderful, fantastic structure, then the states, this impacts our states of water. So the heat of fusion by definition is, remember my little trick, this is how it shows you here is the definition. This is the heat, what's another word, especially in nutrition for heat?
Energy.
Absolutely. So it's the heat or energy released when liquid, I'm going to abbreviate that as LIQ, becomes solid. And this energy cost is 80 calories per gram of water. So this is the cost. This is the heat of fusion. And it's also known as the heat of solidification. And I've worked with some scientists before who consider the loss of heat one of the most expensive things that we do that is inefficient. They call this the cost. This is the cost required to go from a liquid to a solid. So, now it's kind of confusing because what is the freezing point? How is the freezing point different? How is the freezing point different from the heat of solidification? It takes time. For example, do you get water and immediately put it in 100 or 0 degrees centigrade and it becomes solid? It takes time, doesn't it? It takes 80 calories per gram of water. That can happen very quickly or very slowly. And depending on the speed with which you do it, it's going to impact the quality of the product you're making. If you do it very quickly for vegetables, it's called flash freeze, you get a vegetable that's got all the nutrient content of something that is raw. If you do it slowly for vegetables, you're going to lose and it's going to become sort of mushy, kind of what they used to be like before Mr. Birdseye, by the way, Californian, developed flash freeze method. That guy really did exist, Mr. Birdseye, back in the late 1800s. And then if you do it with ice cream too quickly, you get a solid rock and you can't eat it. So you see, part of the food science is knowing how quickly do I want to take something, How quickly do I want this to happen? So you have 0 degrees centigrade, okay? And you want it to become solid. So this is the water. I wish I had a blue, sorry. This is water. And this is sitting at 0 degrees centigrade. And guess what? This is still 0 degrees centigrade. But now it's solid. This time in here is called the heat of fusion, or the heat of solidification, and that's the cost. Now this cost can be impacted. So this freezing point, and we all know that as the molecules of water start getting colder, do they speed up or do they slow down?
Slow down.
They slow down, and so the distance between each other starts getting a little bigger because they're not flying around and touching each other. So the distance is getting a little bit, not much, but just a little bit. And so now there's actually, and if you study this and you actually look at it, it's really kind of cool. There's this development of this small hexagonal openings. Yes, hexagonal. I mean 6. So small little 6-sided openings, and these 6-sided openings you can actually see through a microscope as the water starts becoming colder and colder and colder. Actually, it's getting colder because it's losing calories the longer it sits here. And so it's slowing down. And therefore, as these openings, okay, as these openings become more and more defined in between, what happens to the density? What happens to the density of this water as it finally freezes? Does it increase or decrease? Decrease. Why does the density decrease? Because of these openings, these air gaps. Because of these air gaps. And that's why sometimes if you put a bottle of water in the freezer, it expands. Not too much, but a little bit. And that's because of the lower density. And that's why ice floats. That's why frozen water, which we call ice in this country, floats. Because of the lower density, and it's because of the air gaps. You guys, I want you to remember this. These air gaps is what provides the different types of food we have. It's why that when you fry a potato, it can be crispy. The water in there. Okay? And well, as we get to the heat of vaporization, you'll see what I mean. But that's why it's these gaps that water allows, because of its different states of matter, that creates the functionality of our food. Very important. And then when you're in lab, Wednesday and Friday, we're working with water the whole time and its solubility and what heat does to it. So factors influencing this freezing point. So we're talking about freezing point. And so impact on freezing point. Can I just call that FP? Is that all right?
Sounds good.
Thank you. I'm so glad that you answered me. Thank you. All right, so the thing about is the solutes. The solutes can have an impact on the freezing point. For example, these are just 2 examples. Soluble sugar. Why do I define soluble sugar? That you'll learn in the lab, and those will be in the lab, but there are some sugars that aren't soluble, okay? So there's some that we can find that are insoluble. So soluble sugar and ionizing salt. Both of these will lower. They will lower the freezing point. What does that mean to say lower? Does that mean I have to get it colder to freeze, or I have to, it freezes at a higher freezing point? Yeah, so the more I add to something, the longer it's going to take to freeze, and possibly at a longer, colder temperature, which is why ice cream is going to take longer the more sugar you have in it, the more salt you put in it. Believe it or not, ice cream is very salty. These are all going to impact, those of you who make frozen ice cream, I always do 4th of July, honey, I make the best frozen ice cream. And part of it's because I understand science, and I know when to start, depending on the kind that I'm making. more cream, more fat, it's gonna take a lot longer to freeze. So these solutes are gonna have an impact, and you can see from a food science perspective, that's very, very important. And then other things that affect it are your temperature. This sounds weird, because we're like, well, dude, freezing, you know, but the temperature actually influences the solubility of those solutes. I know. So, in other words, the lower the temperature, the more you're decreasing solubility of most things. So people ask me, why when you make homemade frozen vanilla ice cream, do you heat the sugar first? Do you cook the sugar in the milk? It's because if you add the sugar to the mixture and then try to freeze it all at the same time, it's going to take you forever. Forever. And it may not really ever get solid. That's why some of you who've made homemade ice cream, it's sue me. Okay? Because when you put sugar at a cold temperature, immediately the solubility is reduced. And that's why then sometimes people who make ice cream incorrectly, it comes out grainy. You ever had grainy homemade ice cream? See, now you're getting all the tools to make really good homemade ice cream. All right. And then the pressure is impacted. So I know that sometimes I tend to teach in Boyle's Law. Anybody know Boyle's Law? Bringing back some really bad memories to you. All right, so because the dissolved sugar itself modifies the freezing point, this also then leads to a reduction in vapor pressure. All right, so someone tell me what the heck vapor pressure is. Excuse me?
The pressure, the gas above the liquid.
That's good. He said the pressure of the gas above the liquid. You're saying it well, but I'm going to do a little bit more for people. I can tell you understand it. It's the pressure exerted as molecules of a liquid attempt to become a gas rather than a liquid state. I'm going to write that down for in just a second. But I just want to make sure I add right here that the pressure, the decreased vapor pressure, impacts the freezing point of a product. Okay. And then another thing to sort of know is that I listed salt and sugar. Salt, because it is an ionizer, what does it mean it's an ionizer? Someone got the Nobel Prize for this, not this guy, but someone got the Nobel Prize for explaining dissociation of salt, and thereby that's how we learned about ionizing back in the early 1900s. Anybody know what I'm talking about? It's okay, go ahead and guess. What do you think? Yeah?
You know when you put something in a solution and it breaks something through?
Absolutely, that's exactly what it means. Someone actually had to discover that, which we think, oh, it becomes sodium and chloride. That was a Nobel Prize right there. So the fact that it has that ability to do that, to become separate ions, it actually has an impact per gram that is twice as great as sugar. Twice as great. So it has 2 times, salt has 2 times the impact as sugar. And there's even an algorithm that I had to learn when I was doing the ice cream testing. And basically your book gives you a real easy one. But she tells you that a gram molecular weight of salt in a liter of water depresses the freezing point by 37.2 degrees centigrade. Think about that. 1 gram of salt. 1 gram of salt in a liter of water per liter. What's a liter? It's like 2/3 of a gallon or something like that.
1/4.
A quart of a gallon?
Yeah.
Oh, okay. Wow. See, I'm terrible with metrics. I thought it was more like 2 quarts. All right. Anyway, a liter, not very much, and 1 gram of salt. Every gram of salt is going to depress the freezing point by 37.2 degrees. Good or bad? How about when you put salt on a road? Good or bad?
Good.
That's why salt is put on ice and on a road. as that water melts, the hope is it's not going to refreeze and become ice on the road. That's the purpose of salt, and it's because of this. Every gram of salt reduces the freezing point by how much? I've said it 3 times now. Do you think it's important?
It's very important.
Okay. And then we get to the next state of water. Oh, I really feel like Hercules with this one. All right, yes.
Did you say that salt has 2 times the impact as sugar because it's like about off factors too? So like any
It's ionizing. It's the fact that it can become sodium with a plus charge and chloride with a negative charge. Okay, where sugar doesn't, it's soluble.
Does an ion with that breaks into 3 things have like 3 times the impact?
I have no idea. I don't know what that would be. Give an example you put in food that is that, yeah.
Is the boiling point?
We're about to get, thank you for asking that. I love your curiosity. It's exactly where we're going. See, clearly we're right on track. Thank you. So, so we just discussed the freezing point. So now let's look at the heat of vaporization. The heat of vaporization. And of course, it's got another terminology too. Basically, not terminology, what we're talking about is when liquid becomes a gas, right? We're talking about when liquid becomes a gas. And so this is the heat or energy absorbed in conversion of water, I should say liquid, to steam. And this cost is 540 calories per gram of water. Here's the cost, but this is an absorption instead of release, okay? So basically we're looking at water. I know you guys don't have your phones out. Water I don't draw very good beakers, do I? Okay, so we're looking at liquid water. How did I do liquid water over there? I did it with this orange. Looking at liquid water becoming steam. And clearly we know that this water is going to be boiling to let off this steam. Okay? And the boiling point is 100 degrees centigrade. So once again, if you were measuring water, and those of you in the lab, you're going to be measuring water that's 100 degrees centigrade that isn't boiling yet. Why? This energy cost has not been met yet. And when it does, then you're going to see boiling. Factors that impact the boiling point. So, boiling point. Well, let's define it first. The boiling point is the temperature at which the vapor pressure just exceeds atmospheric pressure. So adjust that for just a moment. It is the point at which the vapor pressure just exceeds atmospheric pressure. So what is atmospheric pressure? Okay, well, you know the numbers, but I'm looking for more of an esoteric definition.
Pressure exerted by air.
Right, it's the pressure we feel around us right now, right? Okay, so when we go to the mountains, what is the atmospheric pressure like there? Much lower, much lower. And what is it at sea level? It's pretty much the highest, okay? So, is the boiling point going to be higher at sea level or in the mountains? Exactly. So I need pasta to cook at sea level. At boiling, I need it to boil, let's say, for 5 minutes. In the mountains, you've just told me that the boiling point is going to be lower. So my pasta is going to boil at a lower temperature than it did at sea level. So do I need to boil it longer or shorter or the same amount of time? I need to boil it longer. Now my pasta, that may not be such a great idea because I don't know how much you like it al dente, but foods that carry bacterial properties, unless they're cooked properly, it makes a huge difference. What atmosphere are you when you're cooking it? Do you know that when you're in the mountains, you need to cook something a little bit longer? Because the boiling point, i.e. temperatures, even if you're not getting something up to boiling, we're always comparing things to boiling point, you're gonna need to cook it a little bit longer. Okay, so basically, let me define vapor pressure for you real quickly here, as a side. Vapor pressure, because it's something that sounds like we should know what it means, but actually it has a little bit more physics to it than you might expect. And it is the pressure exerted as molecules of a liquid attempt to become a gas. E/C, become. So you should never look at water the same again. You should see it as always moving. These are molecules that are moving. And so as water is being heated and is trying to be released from this state here and become erythral, it starts moving faster and faster and faster. Faster, that's what boiling is water moving so fast. And it's exerting all this pressure on all of its partners. Let me free, let me go, let me out of here, let me go. I think of Game of Thrones. Have you seen the recent one? I don't want to be a spoiler here. That thing trying to get to the box, you know what I'm talking about? All right, let me go, and it's trying to get out. You're trying to release, and you're pushing against everything to let yourself out. That is vapor pressure. And when you finally, the pressure that you are pushing on exceeds the atmospheric pressure that's pushing you down and keeping you in it, when you finally have more pressure on you than what's up there, now you are free, and you are steam. So you should think of steam as freed water molecules. I hope you remember that little play. I could just see that. That would be a great play, actually. All right. So in a boiling point, so factors that affect boiling point, factors or impact on boiling point. Let's do the same thing to that we did to freezing point. First of all, clearly, pressure. And we just talked about atmospheric pressure. So the rule of thumb for that one is to remember that for every 500 feet of elevation, boiling point is decreased by 1 degree Fahrenheit. So I'm switching from Celsius to Fahrenheit, forgive me. But this Fahrenheit thing is one I've known forever, and that's what I use as a dietitian, and that's why it's the old way. It's the English. But for every 500 feet of elevation, I think, okay, boiling, and what is the boiling point in Fahrenheit? 212. 212, exactly right. So for every 500 feet, so like I have a condo in Breckenridge, Colorado, right, where we ski every Christmas. And it is at 11,000 feet elevation. What elevation are we at right here in Berkeley? Is it about 200? Let's pretend it's 200 because you're kind of close to the water. In Florida, we're at 0. Where I live, my kids at the beach, you know, we have 0. Let's say we're at 200. All right. So that could be a great question on the exam. If you're at 200 feet elevation and the boiling point, I could make it easy and say it's 100 degrees centigrade, or I could say it's 212. Then what would be the boiling point at my condo in Breckenridge? 11,000 feet. Wouldn't that be a great question? For every 500 feet in elevation, there is a decrease of 1 degree Fahrenheit in the boiling point. I'm sure there's a calculus also for centigrade. I just don't happen to have that memorized. Okay. All right, and the main reason it must be cooked longer, not just taste and whatever, is microbial growth. Okay. All right, and then what about, I think this is something you were going to ask, is what about then sugar, ionizing, and sugar, soluble sugars. Ionizing salts, doesn't have to be sodium chloride, it could be any salt, or soluble sugars. What kind of impact do they have on boiling point?
Same as it have on freezing point.
Exactly right. No. Yes. Yes. Wait a minute. No, the opposite.
No, sorry.
The opposite. It has, yes, it's the opposite. Just it's a different, it has the same impact with a different direction. How's that? Okay. I understand what you were saying. Okay, so in other words, when you add salt, when you add sugar to a substance, you're going to impact its boiling point. You're going to make, it's going to have to boil at a higher temperature. It's going to have to get to a higher temperature to boil. Okay? So it's sort of, in other words, when you add things to water, it's going to lower the freezing point or raise the boiling point. Yes?
So salt raises the boiling point?
Uh-huh. Isn't that funny? More heat energy must be supplied to develop sufficient vapor pressure to boil. So one of the most common wives' tales, urban legends, is that if you add salt to water, it will boil more rapidly. Now knowing what you know, true or false? False, absolutely. The thing that you're thinking of that used to be, because I remember when I was in chemistry in high school, we would add things that had surface area. Do you remember that? Surface area to the water, thinking that by the addition of surface area, for some reason, it was going to impact the boiling and cause it to boil more rapidly. Remember you put those rocks, we put rocks in our things? Does anyone hear that did anyone hear what I'm hearing?
Sweet beans.
Oh, gosh. I was about to say, if one of you are having that much trouble breathing, let me help you. Okay, isn't that amazing how loud that becomes? You know, that'd be another great physics thing to talk about, the funneling of the sound waves. Anyway, all right. So more salt, if you add salt or sugar to your liquid, it's going to need more heat energy to develop sufficient vapor pressure to boil. Okay? And again, in lab, we're going to be doing that. You're going to be adding sugar and salt, and you're going to be trying to freeze, and you're going to be trying to boil. And you're going to see 30 mils did this, 50 mils did that, yada, yada. All right. Any questions about that right now? Yes, sir.
What I was curious about is it the same relation, freezing and boiling?
Is it the same calculus, you mean?
Yeah,
No.
grams of salt per liter.
No, it's different.
Okay.
And honestly, I didn't even write down what it was. Okay. And the main reason is because, and we're going to get to this in the next chapter next week, is because true solutions act differently than when we talk about gels and emulsions and colloids. Yes, we're going to do all of that in here. You remember all that from physical, from chemistry? Yeah. We have to do that. But true solutions act differently. And very rarely in food do we have true solutions. And we tend to boil more in food science than we do freeze. So I don't have that calculus. Your book may have it, so you might want to look that up and let me know. So we'll start up next week with Wednesday with bound water. Okay?